Alrighty, it looks like we are live. Yeah, looks like we're live. Cool, so we'll get started now in that case. So as we talked about yesterday, today's our MATH2901/2801 workshop will be in two parts. Yesterday we covered basically the basics of probability theory. Today we'll be looking more at convergence of random variables, and we'll also be looking into some more stats. And what stats is basically using data and how we can use data to draw conclusions about basically distributions. So that's what today will be about. So without further ado, because we have a lot to cover, we'll get right into it. Okay, so convergence of random variables. So we've seen convergence before. Convergence essentially with real numbers, right? So if we have a sequence like an equals 1 on n, or n equals 1, 2, 3, and so on, then as n gets really large, then informally speaking, this fraction over here becomes really small. So we basically say as n approaches infinity, an approaches 0. And we can actually have the same kind of stuff with random variables. So random variables like x1 down to xn, if each of these has its own distribution, let's just say, for example, xn follows a normal distribution with parameter 0, 1 on n squared, then well, we can basically figure out what happens as n gets really large, right? And that's why we have convergence. But it turns out because random variables are a bit more confusing, they are a bit more complicated, we have a range of different types of convergence. And the first one is called convergence in distribution. And basically, what this is we have a sequence of random variables x1 down to xn, and we want to show that it converges in distribution to this target value, which is x. It's like, for example, in this sequence example, we're trying to show it converges to 0. Very much the same concept, we want to show that xn converges to x. Okay? And it turns out it's actually pretty simple, this method of convergence, because it converges if and only if the CDF of xn approaches the CDF of x. Right, so all you really need to do is calculate the CDF of both variables, and if they are in fact equal as n goes to infinity, then you've shown they've converged in distribution. This second type of convergence is a bit more complicated, but basically we have the same setup, so x1 down to xn, and we want to show it converges to x as we did before. And what we do is we say the probability of this event over here needs to approach 0 as n approaches infinity. What is this event though? This event is that the absolute value of xn minus x is greater than epsilon, which basically means that the probability of the difference between these two random variables being greater than epsilon needs to approach 0. So you can kind of see what this means, right? If basically as we go to infinity, these two variables, they can't be very different, their difference becomes very, very small, then, well, that's convergence in probability. How do we show this? We'll do an example in a second, but basically you want to find this quantity in terms of n and epsilon, and show that as n approaches infinity, that quantity approaches 0. Okay, let's do an example then. So as I said before, we can have a sequence of random variables, and each random variable has its own distribution. Okay, so xn in this case is Bernoulli 1 on n. Okay, and we want to show that it converges in probability to 0. So before we do any thinking, we can just basically go right into the definition. So what's the definition? We want to show that this limit is equal to 0. So let's just calculate that. The probability of xn minus, in this case, x is just equal to 0, being greater than epsilon. And basically what we'll need to do is just calculate this limit, then take the limit as n approaches infinity, and just basically observe that it will go towards 0. Okay, so let's try that. Let's just think about what Bernoulli random variables look like again. They have a probability mass at 0. So we have a probability mass at 0, and another probability mass at 1. I might redraw this actually. We'll just draw the probability mass as a point. And we have another density at 1. over here. So we know that Bernoulli 1 on n means that it has a probability of 1 on n of being here, and the remaining probability, so 1 minus 1 on n, is that it's equal to 0. Okay. So in this case, let's think about what this means. So probability that xn, the absolute value of that, is greater than epsilon. Okay. So if say like epsilon is like a half, we're basically saying this event is equivalent to what I'm shading in right now. Right? So if epsilon is a half, then we can actually see there aren't that many options. Right? In order for the absolute value of xn to be greater than epsilon, we actually can only have it be equal to 1. Right? That's the only option. Because, well, it's not going to be 0, and the only other value our Bernoulli random variable can take is 1. So you can think about this, like if epsilon is less than 1, then, well, this quantity is not that hard. It's just equal to the probability that xn is equal to 1, right? So that's what we'll write first. So consider the case where epsilon is between 0 and 1. Then it's actually really simple. The probability of this event is just equal to the mass at 1, and we know that's equal to 1 on n. And at that point, it just becomes really simple to calculate the limit of that as it goes towards infinity, and we end up getting 0. Okay, so that's our first part, but we still have to consider the other part, because we know that epsilon can be any real number greater than 0. So now let's consider the case where epsilon is greater than or equal to 1. Okay, and that's going to be our next case. If we draw our graph again, the two masses, this is 1 minus 1 on n, and this is 1 on n. Well, if epsilon is really big, so it's greater than or equal to 1, then, well, the probability of this event, so xn being greater than epsilon, is actually equal to 0, because we've basically gotten rid of the option of 1, and there are no, like, possibilities left. So that's our next step. So a Bernoulli random variable can only take values of 0 and 1, so for any epsilon greater than or equal to 1, this probability is equal to 0. And so we can see no matter what, as we go towards infinity, this probability thing converges to 0. Okay, and that's actually the definition. So we write our conclusion, xn converges in probability using this nice notation to 0. Okay, so we've shown, we've done one question basically for that example. Let's move on to some other types of convergence. Okay, so this one is called almost sure convergence, and it says that we've got this sequence of random variables again, and we've got this target value x. Basically, we have that the limit as n approaches infinity of xn needs to be equal to x with probability 1. Okay, and you can kind of see how you might prove this again. You just evaluate this probability and show it equals 1. So it's not really, it doesn't really appear that much in questions, but we'll see it in a theorem later, so it's good to know. Next thing over here, this is convergence in LP. So remember this thing again. So xn minus x, that's the difference between our random variable in the sequence and our target random variable. So what we're basically saying is this difference, as you put it to the power of p, the expectation of that approaches 0. Right? And again, you can kind of see how you might show this. Just calculate this. Then take the limit as n approaches infinity. And you'll end up with 0. And if you can show that, you've shown it converges in LP. Right? And for example, if p is a specific number, so one thing that people say a lot is convergence in L2. Well, that's actually just a special case of this, where p is equal to 0. So we say that the limit, as n approaches infinity, of xn minus x squared is equal to 0. But those are the 4 types of convergence you'll need to know, and they're actually interrelated, right? So there's this nice little idea of convergence strengths, right? So some of these are actually harder to achieve than others. So almost sure convergence is really hard, and that actually implies if you do have almost sure convergence, you also get convergence in probability for free. And then distribution is a bit easier. You get that from P. We also have LP in there as well. So convergence in LP implies P, and that implies D. But you'll notice there's no relationship between AS and LP. because it says over here it's not necessarily stronger or weaker than almost sure convergence. So if you want to draw this out in a diagram, you have AS implies P, that implies D, and also LP implies P, but we don't actually have a relationship over here. And those are our convergence strengths. So for example, if you know something converges almost surely, then if the question asks you, show it converges in distribution, well, you actually get it for free because we know AS implies D. Cool. We'll move on to an actual theorem, and this is a really important theorem in stats that we use. So we start off with a setup of independent and identically distributed variables. That's what IID stands for. They're independent, and they have the same distribution. And we know its mean. We know its mean is equal to mu, and we know its variance is equal to sigma squared. Right? And then we're considering something called the sample mean. So what is the sample mean? Basically, you just take all of these variables, so x1 down to xn, and you take the average of them. So 1 on n times the sum. And the idea is, if you have all of this information, all of these observations from this distribution, the central limit theorem tells us that we can actually work out the distribution of the mean. Specifically, it's equal to this. So n mu times sigma squared on n. So this is kind of intuitive because if you take the expectation of the mean, you've basically summed up all of these random variables with the same mean and divided it by n. So it stands to reason you'll get the same mean. The second part, the variance, that also kind of makes sense because if you take a lot of observations and you average them, then that's not going to have as much variance as just a single observation, right? If I take like 200 people, I average their height, it's very unlikely that the average height is going to be 2 meters, for example. But if I just take one person, it's possible that they'll have an average height of 2 meters, right? So as n gets really big, this variance decreases. Right, but the really cool thing about this is the n part. Right? The central limit theorem tells us that no matter what distribution we started with, no matter what distribution xi followed, this sample mean will always be asymptotically normal. Right? And it'll be normal with, as I said before, mu as the mean and sigma squared on n as the variance. Okay? And so if we recall how we deal with normal random variables, whenever we have a normal random variable AB, if we then take, if x follows that distribution, if then we take x minus a on the standard deviation, which is root b, then we've standardized the random variable. So same thing over here. We've got the sample mean, we subtract the mean, and we divide by the standard deviation. And because the variance is equal to sigma squared on n, the SD is the root of that, so sigma on root n. So another way of writing this is that the sample mean minus mu divided by sigma on root n must approach the normal 0, 1 distribution. Okay. And so this becomes really useful because sometimes when we take the sample mean, we don't know its distribution. We don't know its exact distribution, but what we do know is that it must be asymptotically n0, 1 in this case. So we can use that to get probabilities associated with that. Okay, so let's apply it to an example. So we've got uniform random variables, and bada bing, we've got the mean here over here. Okay, so let's just think about that for a second. We're going to use the central limit theorem because they want us to calculate the probability of this mean being greater than 0.55, and that involves normal probabilities and approximations. So what we'll do is basically start with our setup. So in the CLT, we need to know the variance and the mean of the distribution. So let's just do that. Our uniform random variable, we know its mean and its distribution. So if you check out your formula sheet, which Jerry showed us yesterday, then basically you'll see that the uniform distribution AB, it always has mean A plus B on 2, and variance a 12th of A minus B squared. So we can just apply that to over here. So in this case we've got 0 and 1. So the mean is going to be 0 plus 1 on 2. And the variance will be 1 on 12 times 1 minus 0 squared, which is just 1 on 12. Okay. So we've gotten that to start off with. Okay. And then we can see, using the CLT approximation, all we have to do is just use what we talked about before. So the mean minus what we expect the mean to be, so mu, divided by sigma, so sigma will just be the root of the variance, divided by root n. In this case, that's root 48, because we know we have 48 observations. And then that will be distributed according to n01. Okay, so that's pretty good. That means that basically we've got this approximation to what the mean looks like. So as we usually would, we're trying to find the probability that it's greater than 0.55. So you start with this, then we normalize it, so exactly what we just did. So we subtract a half, divide by root of 1 on 12 divided by 48, which turns out to be 1 on 24. And we do that to both sides. Then this thing becomes a standard normal random variable. It becomes z. And if we evaluate this, we get 1.2. So all we have to do is just calculate the probability that z, a standard normal random variable, is greater than or equal to 1.2. And using your probability tables, it turns out to be 0.1150697. Okay. Now we'll look at a few more theorems. So not only do we have the central limit theorem, but if we do have a bunch of random variables, and even if they're not identically distributed, so in the CLT we had IID. In the laws of large numbers, we just know that they're independent. But we do actually know that they have the same mean and same variance. Then what will happen is the sample mean will converge in probability to the true mean. All right? So it doesn't even matter if they're not normal, doesn't even matter if they're not identically distributed. If they satisfy these properties, it converges in probability to the true mean. Okay? And what that means is that as we take larger sample sizes, as n gets really big, our sample mean will basically more likely be closer to the true mean. The strong law of large numbers is the same, except we have convergence almost surely. And as we talked about before, AS is stronger. So AS is stronger than P, and P is stronger than D. So that's why this is called the strong law of large numbers. Because if you get this one, if you get the strong law of large numbers, you actually get the weak law as well for free. So that's our two laws of large numbers. For the central limit theorem, there's actually a special case of this. So the binomial distribution, essentially the binomial distribution is actually the sum of IID Bernoulli random variables, which we would have talked about last time, which means that the binomial distribution itself, even this number itself, follows the central limit theorem, right? And specifically, because we know that the mean of the binomial random distribution is equal to NP, and the variance is equal to NP times 1 minus P, that means we know that X minus NP divided by the square root of NP times 1 minus P, which is the standard deviation, that's going to be approximately normal. Right, because we're standardizing our normal random variable. We're minusing the mean, we're dividing by the SD. Okay, and that's what this says over here. So we've got a nice example from the MATH2901 exam in 2020. We've got two theatres, they're competing for the business of 100 customers, 1,000 customers, and each customer chooses independently and is indifferent between the two, right? And we're basically using a binomial model to guarantee that the probability of a particular theatre turning away a customer, because the theatre is full, is less than 1%. So when will this happen? Well, it basically happens when we've got more people wanting to go to the theatre than the theatre has, right? So we have n seats. That means that X, where X is the number of people wanting to visit the theatre, X needs to be greater than n. So if we do set X as being equal to this, then the probability of X being greater than n needs to be less than 0.01. Okay, that's pretty good. Let's just set this out formally. So let x be the number of people in any particular theatre. Okay. And we have a distribution for x. First of all, they're competing for the business of 1,000. So 1,000 is our n. We also know that the customer chooses independently and is indifferent. And when a customer is indifferent, it means basically it's just by chance, right? So that means it's going to be binomial, 1,000, a half. Right? So basically, if x has this distribution, we want to require that the probability of x being greater than n is less than 0.01. Okay. So basically, they want us to find a condition in terms of n that will guarantee that the probability of a particular theatre turning away a customer is less than 1%. So we basically evaluate this left-hand side in terms of n. And so basically this is, because we have a discrete distribution, we just sum up all the variables above n, up to 1,000, of the probability mass. So 1 on n, 1 on 2 times to the power of I, times 1,000, I. And this is just the PMF of the binomial distribution. Okay, and so we've got that over here. And basically we simplify to get that this thing over here needs to be less than 0.01. Okay, very fun. Moving on to B. So we want to basically explain how a binomial distribution can be approximated by a normal distribution. So not really a complex question, but basically the idea is that this equation by itself looks really scary. It's actually pretty hard to solve. So what we want to do instead is we want to use the normal distribution instead. So solving for n is not super easy. And that's why we're not actually being asked to solve in part A. Instead, we have from the mean and variance of the binomial distribution that this theorem holds. This is what we saw before, and that's what we're going to use. Okay, so again, we want p of x is greater than n is less than 0.01. Let's write that as a binomial expression, right? Because x is binomial, remember, 1,000 people times a half. So n equals 1,000, p equals a half. So we'll actually get x minus np, which is 500, divided by root np times 1 minus p. And then that has to be greater than or equal to n minus 500. Oh, actually, I'll just rewrite this. So x is binomial 1,000 a half. And so that means that this thing, we can standardize it, is equal to the probability that x minus 500 divided by the square root of 1,000 times a half is greater than doing the same thing on the right hand side, n minus 500 divided by 1,000 times a half. And that's pretty good. Okay, so that means that we've converted this thing to just a standard random variable z, and then this thing over here becomes an expression in terms of n. That's pretty good. That means that we want z, probability of z being greater than n minus 500 divided by root 250. All right, and at this point, let's just try to draw a graph to make it a bit clearer. So any standard normal random variable, I'll just write x, and this is the probability mass density function. It'll look a bit like this. But basically what we're saying is that we want to find the number over here, n minus 500 divided by root 250, needs to be a number such that the probability of everything being greater than it is less than 0.01. Okay, so in other words, n minus 500 on root 250 needs to be the number here such that this area is 0.01. Right? And there's actually a name for this number over here, this x value over here. It's called a quantile, right? The quantiles mark out certain points in the graph where the area above or below them is equal to a certain value. Specifically, this is called the 99th quantile. It's kind of like percentiles, like when you're talking about ranking people, right? If you're in the top 1%, you're at the 99th percentile. and that's actually the quantile at 0.99, right? So the question that was in this paper provides this information, right? Q norm is an R function. You don't need to know how to program using R, but you need to know how to read it. Q norm is just the normal quantile. So basically, this is just saying the 99th percentile of the normal distribution, right? So they give us a number of them, but it's a bit of a trick because we only need the first one because we need it to be less than 0.01. So this is the number over here. We've solved for x. So I'll just write this out. This number over here is equal to 2.326348. Okay, fun, fun, fun. So we'll be using the top result. So we continue down. So that means that n minus 500 on root 250 needs to be equal to this number over here. So we've just shortened it to 2 decimal places, but 2.33. Okay. From then on, we just easily solve for n being equal to 537. And in this case, we actually won't get an actual integer as our answer, but what we then do is we round up, by the way. So we need to round up. Because remember they said we want the probability to be less than 1%, so we have to get it a bit higher than the exact value. So just a bit higher up there. Cool. So each theta needs to have at least 537 seeds. Okay, this is Slutsky's theorem, and this theorem is talking about two random variables that converge in different ways. So xn converges in distribution, and y converges in probability. And specifically, y converges to a constant. Basically, what Slutsky is saying is that if you add these two, you actually still get convergence in distribution, but this time to x plus the constant. So you can just replace yn, it converges to a constant, you can just replace it with c. Same thing if you multiply them, you can just replace the yn with c. This becomes useful in algebraic manipulations when you're trying to show convergence in distribution. But we won't do an example because really it's just replacing yn with just c. Cool. All right, we're talking about a delta method. So immediately we've got the sequence of random variables such that yn minus theta divided by sigma on root n is n01 distributed. Okay. So it reminds us a bit of the central limit theorem because we had before the sample mean minus theta or mu or whatever you want it to be converges to n01. Okay. So if it converges to n01, this should be a convergence in distribution, then we can actually take any function of yn that's differentiable. So suppose that g is differentiable in the neighborhood of theta, right? And also that it's not a stationary point. If that's the case, then we can actually work out the distribution of g of yn, right? So it doesn't matter what g is as long as it's differentiable, we still just get g yn. Well, its mean is going to be g of theta, which kind of makes sense. And also its variance is going to be this thing. Well, its standard deviation is going to be this thing. So remember, the standard deviation of yn was equal to sigma on root n. But if you take the function of it, so g of yn, then what you basically get is the variance is equal to the original variance times the derivative of g. And that kind of makes sense because if we plot like y on this x-axis, we plot g of y, and let's say g of y has a really big gradient, right? So a really high gradient. Then, like, if we have a small variance in y, if g prime of y is going to be really big, then that means that the variance of g is going to be a lot bigger, right? Specifically, it's going to be g prime of y bigger, right? So that's when we multiply by g prime, because the derivative is kind of a measure of how much this function changes as y changes. So if y moves by 1 unit, it has a variance of 1 unit, then this thing over here will have a variance of 1 times the derivative g prime of y, right? And that's why we get this. So the delta method tells us that the mean becomes g of theta, and the variance is multiplied by the derivative. Cool. So a nice example with gamma random variables. So the first one is just trying to find out the distribution of the sample mean, right? Because yn is our sample mean, right? We've got independent random variables, they're IID. So you guessed it, we're going to use a CLT. So before we can actually do anything, remember the central limit theorem requires us to know mu and sigma squared. So we zoom into the gamma distribution, and we had, remember, gamma A4. And what we're basically doing is we're trying to find out its mean and its variance. So they've got a nice formula for us here. Alpha beta, that's the product of the two parameters. So our mean is going to be equal to 4a. What about variance? Same thing, they give us a nice table for it. It's going to be alpha beta squared, so a times 4 squared, which is equal to 16a. Okay, so we're good to go. We've got mu, let's just think that over there, and we've got sigma squared. Okay, cool. So what that means is actually, let's state the central limit theorem. So yn, which is the sample mean, minus mu, so 4a, divided by sigma, let's not use 16a, whoopsies. Not sure what just happened. Oh, that's better. Yep, so yn minus 4a, divided by, we don't use the variance 16a, we actually use sigma itself, so root 16a, and of course we divide by root n. And that's going to conversion distribution to n01. That's pretty good. We're actually not there yet though, because they write it in a bit of a different way. But you can see that, well, what they've done is they just moved root n to the top. So we take this. And that's really close. The only difference is that we have a root 16a on the bottom, they don't. Well, that's really simple. We just multiply through by root 16a, and convergence and distribution, we can just multiply through by constants. So all we've got to do now, basically we've done all this. All we have to do now is just multiply through by root 16a, and we get from there to there. And also, we go from n01 to n016a. And why is it not root 16a? Because we know that if we multiply a normal distribution by a constant, we do multiply the mean by that constant, but the variance kind of has a squared relationship, but instead we get sigma squared times c squared. So we multiply this through by root 16a all squared, which is perfect. Cool. All right, so you can kind of sense where this is going because, well, number one of the title, because of the title, but number two also because now we're taking the function of yn, okay? We're going to use the delta method, okay? So in this case, g of x is equal to e to the x because we're going from the distribution of yn to the distribution of e to the yn, okay? So g of x is equal to e of x, and that means that we have to take the derivative to get e to the x. Okay. So let's write out the delta method again. So we know that e to the yn, it approaches e of the original mean. So that's e to the 4a. So looking good so far. Then we divide by sigma on root n, so root 16a divided by root n. But we also multiply, if you remember, by the derivative of this function g at the mean. Right? So that means we get e to the 4a over here. And that is n01. So just as before, we can just multiply through by these two things, except this time we have to get rid of both of these. So we multiply through by that, and we get e to the yn minus e to the 4a times root n. It needs to be normal 0, and then we've got 16a, because we've got this squared, times e to the 4a squared. And it follows on pretty nicely using our index laws that that's just equal to 16a, e to the aa. Okay. So yeah, we're now trying to find the convergent distribution of e to the yn. So you can read through this in your own time. Basically, we've got the delta method, right? Evaluate that, and we just get this. Cool. And that's the end of our first topic. Now we're going to look at estimators. So this is a new kind of concept, but let's just start with the setup. So we've got x1 down to xn, that they're identically distributed random variables, and they have a common PDF. And what is this notation? Well, remember before when we had like our gamma, alpha, beta distribution? Basically, this is a distribution that depends on two parameters, so like two variables, right? And in this case, we don't actually know what it's going to be, right? And this is very practical, right? It's a very practical situation, right? Because for example, like when you observe like heights, or you observe like certain properties of things, right? No one's out there telling you, oh, this is a gamma 3, 4 random variable, right? Often, maybe you'll know it looks a bit like a gamma distribution, but you want to try to find out what these parameters are. So that's the setup over here. We don't know what the parameter is, but we're going to try to estimate it, hence the name. So what is an estimator? It's any real valued function of the observations. So remember we have observations x1 down to xn. The estimator is equal to any function that takes these random variables and outputs a single number. So g goes from Rn to R. And that seems a bit underwhelming because how is that supposed to help us estimate it? Well, the idea is that this is the definition, but if we want a good estimator, then somehow, in some sense that we'll soon see, the estimator needs to be approximately equal to theta. Right? A classic example is a sample mean. So we know the sample mean of maybe a normal mu sigma squared distribution. It actually it's approximately equal to mu, right? We learned that through the law of large numbers and also through the central limit theorem. But basically, xn is approximately equal to mu. So a good estimator would be, for example, the sample mean, because that takes our observations and divides them by n, right? And that is a function, that's a valid estimator. But we'll see that there are lots of different types of estimators. So the function of the estimator is to estimate theta, and for it to be effective, it will need to have certain properties. And we'll look at those just now. So before we actually look into the actual properties, just a bit of a disclaimer. This is actually a random variable. It's not a number, it's a random variable, right? So for example, the sample mean, this estimator, it's a random variable itself, right? So it can vary as well, right? We might not get mu. If you take a really bad sample or a really whack sample, right, it's not going to be equal to mu, right? It can take a range of different values, hence why it's a random variable. And consequently, it has its own probability distribution. And you can often calculate it from the distribution of x1 down to xn. So for example, Jerry yesterday talked about the distribution of a max or a min of random variables, right? That has its own distribution. Another example is a classic sample mean. The central limit theorem tells us that it's approximately normal. It's not equal to just one number, it's approximately normal. So we'll get into the concepts that we actually need to talk about. So estimator bias. So theta hat is an estimator of theta. So we don't have to write theta hat. So for example, if you're trying to estimate the parameter alpha, the estimator for this is alpha hat. If you're trying to estimate mu, the estimator is mu hat. Right? Basically, we're just doing this with theta hat, an estimator of theta. So the bias of the estimator is equal to the expected value of the estimator minus theta. And you can kind of guess we don't want this to be a super crazy big number, because otherwise we're way off, right? If the expectation of our parameter is way different from our actual parameter, well, something's gone a bit wrong, right? Something's gone a bit haywire. So that's why we have this concept called an unbiased estimator. If the bias of this is equal to 0, then we're happy, right? That means it's actually going to be approximately right a lot of the time. So theta hat is going to be an unbiased estimator of theta. Cool. Let's take an example. Right, suppose x is a discrete random variable with mass function p of x. Right, and suppose it has a finite space. So we've got this space which basically means it can only take values a1 down to am. And again, we've got IID samples. And we've got this formula for the estimator, right? So the estimator of P of AJ is equal to 1 on n times this curious little thing. This thing is an indicator function. And recall that the indicator function is either equal to 1 or 0. It's equal to 1 if AJ is equal to xi. It's equal to 0 if not. Okay, that's pretty good. We've got our definitions down. So basically what this is doing is basically summing up for all of our different observations, whether or not xi is equal to aj. So if none of them are equal to aj, we get 0. If 4 of them are equal to aj, we get 4. So this is kind of makes sense, right, why this is a good estimator, because we're basically counting how many of them were equal to aj, dividing them by the total number in the sample. So that's going to be approximately equal to the probability of getting aj. But we have to show it rigorously. So to solve these kinds of questions, we want to try to find the expectation of the estimator. And once we've done that, because the question is getting us to show it's unbiased, we want to show that the expectation is actually equal to what we're trying to calculate. Okay. So the expectation of p hat of aj is equal to the expectation of the sum. And the first step with these kinds of sums is always just to take the expectation inside. Basically now we get 1 on n times the sum of the expectations. And now we come down to a problem. So what is this? This thing, recall, I said it above, is equal to 1. Oh, I accidentally rubbed it out. If xi is equal to aj, and equal to 0 if not. So what's its expectation? Well, this looks like a Bernoulli random variable. So Bernoulli random variable. What's the parameter? The parameter is going to be the probability of getting 1. And in this case, that's just going to be, by definition, the probability of getting aj. Okay? So that means that each of these little things is Bernoulli P of aj distributed. So you can read through this in your own time, but basically the distribution of the indicator function is just equal to a Bernoulli random variable. And specifically, it's going to be equal to P of xi is equal to aj, or as we said before, P of aj. Because we know that the expectation of Bernoulli is equal to P. Cool, to sum it up, we get the sum of n p aj's, and hopefully this is something we've done before. If you sum up a constant n times, you just get n times that constant. So this works out to be 1 on n times n p of aj, which is just equal to P of aj. Cool. So the last step is just to calculate the bias, which just means take this and subtract P of aj, and then you'll get 0. And so that implies that this thing is an unbiased estimator. Alright, so the question isn't over, because looking back, not only do they want us to show it's an unbiased estimator, but they want us to compute its variance. So because p hat is actually a random variable, it has a variance as well, so this question makes sense. So all we have to do is calculate the variance of this sum. Right? And each of these is Bernoulli, and we know that Bernoulli has variance p times 1 minus p. If you don't remember that, you can check your formula sheet, but basically it has variance of p times 1 minus p. So in that case, in this case, because we know what p is p of aj times 1 minus P of aj. And because, so we're taking the variance of this, and because we know that they're actually identically distributed and also they're independent, we can actually take out this constant first. So first of all, this constant comes out and it becomes a square, because variance has a square relationship. And then we get the variance of the sum, but because they're independent, we know this property that variance of x plus y, if x and y are independent, is equal to variance of x plus variance of y. So basically this variance of the sum turns into the sum of the variances. And you can always do this for IID samples. And so this becomes P of aj times 1 minus P of aj, and then you end up with this thing over here. Okay. So it's just similar to the kinds of calculations we've done before, except now we have the context of estimators. Cool. So we've just seen that since an estimator is a random variable, it also has a variance. And do we want it to be big or small? Well, that kind of makes sense that we want it to be small, because then we get a similar value every time. There's also this idea called standard error. And standard error is just the standard deviation of the estimator, right? And it's equal to square root of the variance, right? This kind of concept is a bit difficult though, because let's just take this example. Let's just say we want to know the variance of our estimator. And in this case, it's equal to P of Aj times 1 minus P of Aj divided by n. But the idea is we don't actually know P of Aj. That's what we're trying to estimate. So if someone asks you for the variance of the estimator, and you tell them, oh, it's P of Aj times 1 minus P of Aj divided by n, well, that's not very helpful, is it? Right? So what we often do is we basically replace this with the estimate of that random variable. So we'd replace this with this. Right? So if someone asks you for the variance, you can give them this in terms of your actual expected value. That's what this means. It's difficult because the variance is often a function of the parameter itself, right? So we substitute in our estimate for the parameter. So that's what this line over here means. It's equal to the square root of the variance, where we sub in theta with the estimate over here. Cool. The next concept is called mean squared error. So MSE, or mean squared error, is equal to the expectation of theta hat minus theta, all squared. So basically, this is how off we are. Ideally, if we had a perfect estimate, then theta hat would always be equal to theta. But because it's a random variable, that's not going to happen. So basically, we want to find out how much it differs. How much it differs, right? So how much it differs and the expectation of that, right? And we want this to be small again because we don't want to be way off. And you can actually show that this combines the two concepts we've talked about. So it's actually equal to bias squared plus variance, right? So having looked at that now, we've got a useful metric that combines these two concepts. So if we have a low MSE, it means we also have a low bias and a low variance. So in general, we kind of can measure how good an estimator is by looking at its MSE. Because if the MSE is low, then we're effectively minimizing the shared contributions of bias and variance. Cool. So in this case, it's a really nice question. We've got two different estimators, and we want to show first that they're both unbiased, but then we try to compare the two estimators, right? So what that basically means is there a metric we can use? Well, yes, so we can use MSE. So for part 2, we'll use MSE to compare the two estimators. Okay. So, first of all, you have to show their bias though. So, let's look at this first. To calculate bias, we always start by calculating expectation. So the expectation of this thing, well, we actually need to start from looking at the distribution of this thing. So, well, this is just a constant, but what about this? We can start by calculating the distribution of the maximum. And Jerry actually walked us through how to do that, so I'll just show you very quickly. But basically, we need to find the PDF of the maximum, and we always start with the CDF. And we start with the CDF because then we can actually break it down into probabilities, right? So the probability of u being less than or equal to u is equal to the probability of the max of these random variables being less than or equal to u. And that's actually just equal to the probability that all of them are less than or equal to u. So we actually can express it as a product of all of these different probabilities. And that means that we can express it as a product of the individual CDFs. So the CDF is nice because the CDF of a maximum is the product of individual CDFs. Cool. All right, and that means we have to actually calculate the CDF. I won't go into it, but because this is uniform 0 theta, you can actually easily calculate the CDF to be equal to u divided by theta. And so all you have to do is just sub that in. You get that this, the CDF is equal to the product of n of these, which is just equal to 1 of these to the power of n. And that means you can find out the PDF. And then once you've gotten the PDF, you can then integrate the PDF and you'll get theta. Right, so I'll walk you through the steps. Basically, the expectation of theta hat is equal to n plus 1 on n times the expectation of the maximum, right, which is equal to all of this times u on the interval 0 to theta. Calculate that and you'll end up with theta. And you'll work out that theta hat is equal to an unbiased estimator, because that means that the bias is equal to expectation of theta hat minus theta. Cool. Alright, so this next one is actually a bit simpler as well. So because we've got the sample mean, hopefully we've done this like a lot of times, but basically the expectation of the sample mean, you can always take constants out. Now express this as a sum. And once we've done that, you can actually replace the expectation of the sum with the sum of the expectations. Right, and each of these, because it's uniform 0 theta, will be equal to theta on 2. So basically this just becomes 2 on n times theta on 2 times n. And if you actually cancel this all out, you just get theta. Cool. And the working out is very much the same. Basically the expectation of the sample mean will always be equal to the expectation of just one of the observations, which is theta on 2. And so if you just multiply by 2, you just get theta. And that means that the theta tilde is just going to be unbiased. Alright, back to the question. This is where the fun begins. We want to show which of the two estimators is better. So let's look at these two estimators. And to calculate MSE, well, we could calculate, remember the formula, this, but let's just take a step back, because we can actually calculate this is equal to bias squared plus variance. And because bias is 0, we can actually just say this is equal to the variance. That simplifies things a bit, and that means to compare these two estimators, we just want to compare their variances. Cool. Alrighty. So back to this. So we've got, we'll start with the easier one. So we've actually done this a lot of times, the variance of the sample mean, because remember from before, if you actually take the variance of the sample mean, let's just calculate that. You can take the n out, and you get 1 on n squared, and then you can replace the variance of the sum with the sum of the variances. And that means the variance is going to be 1 on n squared times n times the variance of just 1. And that cancels out to be 1 on n times the variance. Right, so that's what we've done over here. Basically, we've just done 4 times the variance of x, the sample mean. Then we've taken out the n, and we replace this with the variance of just one observation. And you can actually calculate this using the uniform table. So remember I said before, the mean of the uniform random variable is a plus b on 2. The variance is equal to a 12th times a minus b squared. And that's just going to be a 12th times theta squared. That's where this comes from. And you end up with just 1 on 3n times theta squared. Cool. Alright, so now we're looking back at the other one. So it's actually the same concept. All you have to do is just take the variance of this thing. And to do that, you just take out the constant and you square it. and then you take the variance of the maximum. How do you take the variance of the maximum? Well, it's pretty simple. You just look at the PDF, and simply you just calculate expectation of u squared minus the expectation of u all squared. Right, and you'll get this minus that, and that gives you a nice little algebraic expression over here, which we won't go through because of time. But then all you have to do is just calculate the variance and just compare them. So, well, the variance of this one is equal to this. That's what we got in the end. But the variance of the other one, if we remember, variance of theta tilde was equal to, let's just get it up, 1 on 3n times theta squared, right? And so basically we want to compare these two things as n goes to infinity. So which of these gets smaller as n goes to infinity? Well, from first year calculus, we remember that this one has degree 2 on the bottom, this one has degree 1 on the bottom, so naturally this one will go towards 0 real quick. Okay, and so that's why we've written this notation. Don't worry if you don't understand this, but basically you can just simplify this a bit. We've got variance of theta hat is less than the variance of theta tilde, and that means that the one with the smaller variance is also the one with the smaller MSE, and therefore it's a better estimator. So that was a long question, but most of it was just calculations, which we skipped through. So hopefully the concepts all make sense, and you can visit the calculations in your own time or try them out yourself. Okay. Now we'll look at asymptotic properties of estimators. So the estimator sigma hat is called consistent if it converges to theta in probability, which is good because then it means that approximately, as n gets really big, this basically becomes equal to theta most of the time, right? And you can show, another way you can show this is if the MSE of an estimator approaches 0, then it's consistent as well, right? And why is that? Because MSE of theta hat is equal to MSE is equal to the expectation of theta hat minus theta all squared, and that actually approaches 0, then that means this is convergence in L2. Right, so if you've got convergence in L2, we learnt before, that means you get P for free. So an alternative way, if you don't want to do convergence in probability, is to show that the MSE approaches 0. So for example, looking at this, this approaches 0, and also the other one approaches 0. Well, I can't find, it's over here. Basically, both of the variances of the estimators we just talked about both approach 0, so it means that they're also both consistent. The next one is called normality. So an estimator sigma theta hat is asymptotically normal if you take theta, you subtract the actual value of theta, you divide by the standard error. What does that look like? It looks like standardization to me. If that's approximately n01, then that means that theta hat is approximately normal. So wait until you find out about MLEs. You'll be excited to learn that those are approximately normal. So we can also use approximations for that. Cool. All right, and that leads nicely into our next point, which is about estimation and inference. So this is all about applications of estimators, because it's all well and good to have them, but because they're random variables, they won't always equal the actual parameter. And in fact, if the estimator is continuous, then the probability of theta hat equaling theta is actually equal to 0. To resolve this issue, we have this concept called confidence intervals. So what is it? It's basically saying, well, theta is not going to be equal to the actual estimated value. Let's say we get this is equal to 5.3. It doesn't mean you can go around telling people that theta is equal to 5.3, right? It's not going to be true all the time. So what we want to do is basically construct a confidence interval, which captures a range in which we're pretty sure that theta hat lies, right? So for example, I can say, I'm pretty sure it lies between 5.1 and 5.4. Right, I can tell you that, right? And you can say, I know this with a confidence of 95%. What does this number actually mean? Is it just something I pulled out of nowhere? Well, generally when we say we're 95% confident, it means there's a 95% chance that we actually got the right confidence interval, which means that theta is actually inside. So one thing that people always say is that 95% of 95% confidence intervals capture the true parameter. You're never going to be 100% sure because some distributions, they go all the way to infinity, right? So it's always possible that you're just way off. But what we're basically saying is that 95% of the time, we will have the real parameter in there, right? And so the bounds of the confidence interval are also random variables because we get them from the data as well. But that's what a 95% confidence interval means. So more formally, we'll take a sample, x1 down to xn, on a random variable x, where x has a PDF given by x and theta. And let alpha be specified. Okay, it's just a number between 0 and 1. And we've got two statistics. L is called our lower bound, and U is called our upper bound. So we say that LU, which is the interval from L to U, is a 1 minus alpha 100% confidence interval. So in the example I just gave you, alpha was equal to 0.05. And we say that's true if the probability of theta lying between L and U is equal to 1 minus alpha, right? And so we call 1 minus alpha the confidence coefficient. So in our example, it was equal to 0.95. Right, so hopefully that kind of quantifies everything. So it's a confidence interval because we're reasonably sure that theta lies within the confidence interval. We'll take an example. Okay, we've got x1 to xn, a sample from the n mu sigma squared distribution, where sigma is known. Then this is a confidence interval for mu. The sample mean is in the center, and we've kind of gotten these kind of error terms, right? If we graph this on a graph, this is x mean, and we've gotten these two error terms. So this notation, by the way, we'll talk about in a second. Basically, these are error terms. So that means our confidence interval is between here and here. So although this is a good estimator, we can't say that mu will be equal to x bar. What we're basically saying is we're reasonably sure it lies between these two bounds. Cool. So we'll break it down. This is a sample mean. This is the known, it should be standard deviation. And this, let's just be very clear, is the 1 minus alpha on 2 quantile of the N01 distribution. So what does that mean? Basically, remember our quantiles are percentiles from before? This number is equal to the number such that we have below it 1 minus alpha on 2 and above it alpha on 2. And basically what we're saying is that this number over here is equal to z on 1 minus alpha on 2. So how do we even get this formula though? Right, because it looks really nice, but how do we get this formula? Well, there's actually a really simple procedure you can always use to get confidence intervals. So start with your estimator sample mean, right? In our example, we want to find a simple distribution that does not include the parameter in it that x bar can be reduced to. So remember x bar is equal to n mu on sigma squared on n. Because we know that x is n mu sigma squared. So if you take the sample mean, it stands to reason that you just divide the variance by n. Well, that's a nice distribution, but you can't do much with it because you don't actually know what mu is. So what you need to do is find a simple distribution that does not include the parameter in it that we can reduce this to. So well, let's think about it. How do we get rid of mu in the distribution? Well, we've done this a lot of times before, right? You just standardize it. So x bar minus mu on sigma on root n is going to be n0, 1. That's a good start, because now we've gotten this simple distribution that everyone knows about. This is our favorite distribution. Right, it's our favorite. And that means we can try to find, for example, bounds over here. So what we say is then, we've done this over here, we find the quantile values of the normal distribution that would imply a 1 minus alpha confidence interval, right? So we know that z, so the z, the standard normal random variable, can be said to lie between two numbers with probability 1 minus alpha, if we define these properly. So remember from before, we want to have an interval that kind of has bounds on both sides. So we're trying to solve for these two cuts. These are the two cuts, L and U. And if we want the probability of this statistic lying between these two numbers to be equal to 1 minus alpha, then what we do is we segment the probability onto the entire graph into 3 sections. So we say in the middle we've got 1 minus alpha. Well, what do we need on the bottom? We need, well, the remaining probability is alpha, so we need alpha on 2. On the top, we've also got to have alpha on 2. So to get these bounds, they're actually going to be equal to the quantiles. So this one is going to be the alpha on 2 quantile. This one's going to be 1 minus alpha on 2 quantile. Right? And that's what we've written over here. So we know that 1 minus alpha is equal to the probability that this beautiful thing, this standard normal variable, lies between these two quantiles. That's why we get this beautiful thing, 1 minus alpha on 2, because we're trying to divide the remaining probability, which is alpha, into 2 parts. Right, and that's all well and good, but we don't have a confidence interval for mu yet. So what we do is we try to make mu the subject of this equation. So I'll write this out again. Add a blank page. So it's a very big blank page. Basically, we want to make mu the subject of this. That's always going to be our aim, because our aim is to basically find two numbers such that the probability of mu lying between them is equal to 1 minus alpha. So you take this thing over here, and you try to make it the subject, right? So let's start with this over here. Okay. Let's make mu the subject by multiplying through by this. That's pretty good. But mu is still not the subject, unfortunately. So maybe let's subtract this thing over here. Mu still isn't the subject, but you know what we can do? We can just multiply both sides by -1, invert the signs. And we've got a confidence interval, right? Because now we're saying that the probability of mu lying between these two numbers is equal to 1 minus alpha, which is what we need. So therefore, this thing over here is the lower bound, and this is our upper bound. Right? So that's where we get this confidence interval over here, which is this really, really annoying expression. Basically, it just comes down to the fact that we want to find quantiles for the normal distribution, and basically make mu the subject. Okay. Cool. And that's what we've got over here. So we end up with this is what we need. and that gives us a confidence interval. Now we'll look at the student t-distribution, and this looks really complicated. It's actually not too bad because you don't actually need to memorize this, but this is just a separate distribution, and you'll find it actually looks a bit like the normal distribution. It is symmetric as well, but it's just a bit different. Why do we care about it? Because you know how before we were saying that the sample mean minus mu divided by sigma on root n, it follows an n01 distribution? Well, we don't always know sigma, right? Sometimes we have to estimate it. So an estimator you would have seen before is the sample standard deviation. So the sample standard deviation is equal to the sum of the squared deviances divided by n minus 1. And what we basically know is that if we take x bar minus mu and we divide by, instead of using the actual standard deviation because we don't know that, we divide by the sample divided by root n, that's not going to be normal exactly. It'll approach the normal distribution as we get a really, really big n, but it's not always going to be normal. Instead, it follows what's called a student t-distribution with parameter n minus 1, but we don't use the phrase parameter, we say degrees of freedom. So we say that this follows a t-distribution with n minus 1 degrees of freedom. Okay, cool. And that means that if we don't actually know the variance of a normal sample, we actually have to use the sample standard deviation instead, and that means we also have to use the t-distribution instead. So it looks really similar, except before we had, I'll write it out, we had z, 1 minus alpha on 2 times sigma on root n. Now, instead of sigma, we have the sample standard deviation. Instead of the z quartiles, the normal quartiles, we have tn minus 1 quantiles, right? So I'll just go through all of this. It's the same thing, except because we know that this thing over here follows tn minus 1, you can probably sense we use the same method, right? We said x minus mu on sigma x on root n. It lies between the two quantiles, so t n minus 1, 1 minus alpha on 2. It lies between these two things with probability 1 minus alpha, right? That's the same concept we used before, because before we said that the normal random variable, it lies between tn minus 1, it lies between the quantiles of the normal distribution. Now we're saying this thing over here lies between the quantiles of the t-distribution. And you can probably sense that what we did from there was we made mu the subject, and we ended up with this. That's a really, really quick proof, so don't worry too much if you didn't follow it. But basically we use the same method, right, to form the confidence interval. Except now, we can't use normal because we're using the unknown variance. Instead, we have this confidence interval. Cool. We'll start this question in a second. I'm just going to get a charger, and that's a good place to take a break, maybe a 1-minute break, while I get my charger. Just give me a few seconds. We'll be right back. Alrighty, so you'll notice I'm in a slightly different place, and my laptop, I think, kind of crashed in the middle, and also my iPad started going in portrait mode because I was moving around. But yeah, we're back to do some more cool stats. There's a comment from, I believe, Marty. So yeah, the exam is online, so you could use R as long as that's allowed for your particular course, instead of using the tables, which is quite nice. Cool. So we'll go back to our confidence intervals. Alrighty. So this is a bit more of a complicated question, but basically we've got a new density function, and we're trying to find a confidence interval for lambda. Okay. So the first part of the question is just to show that xi squared follows a gamma distribution. So this is actually unrelated to what we've just talked about, so I won't go too much into it. But basically we start with the CDF, because if you start with the CDF, you can find the probability that x squared is less than or equal to x, and reduce that to something in terms of x. And once you've gotten that, you can basically just use the CDF of your density function here. So we'll do that. Yeah, so it becomes fx of root x. And then all you have to do is just evaluate the CDF by integrating the PDF, and you get 1 minus lambda pi u squared. And what you end up doing what you end up doing is you get you sub in root x, and then you get the CDF of a gamma random variable, right? Because you just look at this, you get 1 minus e minus lambda pi x, and if you want to, you can actually just calculate the PDF. That equals lambda pi e to minus lambda pi, and you can compare that with your lookup tables in the exam, and you'll work out that that's going to be gamma 1 on 1 minus pi lambda, right? Again, not related to what we just did, but it's a necessary precursor to this. Okay, cool. So similarly, we've got the density function of this thing over here. So we've got a sum of a bunch of independent random variables, so we can use the MGF method, right? I suppose you could try to use convolutions, but convolutions are really difficult when you have more than one random variable, so it's much easier to use the MGF, right? So first of all, the MGF of one of them is equal to this, because we've got a gamma distribution. And then what we do is we basically have the moment generating function of t is equal to, just express it in the expectation form. Then you can just try to break it up, right? So we've done that already. You've got the expectation of this sum can be thought of as a product. And then, because they're all independent, you separate out the product. So hopefully we've done stuff like this before. If you've got the expectation of this sum, you split it up into a product, and then you take the expectation inside. And then you end up with some term in terms of the moment generating function of xi squared. In fact, you've got e to the xi squared times pi on n times t. That's actually equal to the moment generating function of xi squared, where you sub in pi on n t. Okay. And then you just sub it in over there. Because we've got the product of n of them, we just put it to the power of n, and then we just sub this into our original moment generating function. So remember, mx of t was equal to, let's just chuck it in, xi squared was equal to this. Then you take this to the power of n, or first of all you have to sub in t times pi on n, and you'll get 1 minus t times pi on n divided by pi lambda. And then you just put it to the power of n because you've got a product of n of them, and you end up with this thing over here. Right. So again, we didn't go through that thoroughly because this is stuff we learnt about last time, but you end up with this thing over here. And that is the MGF of the gamma n 1 on lambda n distribution. If you have any questions, you can write it in the chat and we can go over it after. But basically that's just what we did last time, so I won't go too much into it. And then they want us to find the density function. So once you know the distribution, which is gamma n 1 on lambda n, all you have to do is just find the PDF of the gamma distribution from your little from your formula table, and you end up with what they want over here. Okay, this is the part we'll go through thoroughly because it's relevant to what we just talked about. We want to find a confidence interval for lambda. Okay, and so we'll start off with an estimator of lambda. So in the question, let's just go back to the question. They gave us a bit of a hint. A useful estimator of lambda is equal to lambda hat equals this. Okay, so in your confidence interval, you generally start with an estimator of that random variable. So basically what we've got then is we want to find this in terms of what we've done before. So if you compare this with t from just then, you find that this is equal to 1 divided by t. So that means that our starting point is basically 1 on t. So this is equal to 1 on t. Okay? And so what we basically want to do then is just try to find a distribution in terms of this estimator that is, remember from our steps before, find an estimator, then find a function of the parameter that has a simple distribution that is free of the parameter, right? So try to take this thing over here and reduce it to a distribution that doesn't have lambda in it. So first of all, that means that 1 on lambda hat is equal to t, and that has, remember from before, it has a gamma n 1 on lambda n distribution. Cool. Well, that's not free of lambda, which is a bit problematic, because we'd rather it be free of lambda, because then we can construct the bounds of this thing, right? So if it does have lambda in it, and we don't know what lambda is, it's a bit hard for us to find the lower bound and the upper bound for this, right? In order for us to find lower and upper bounds, remember from before, I'll go back to that massive sheet of paper. We started with the quartiles of the normal distribution, and we can actually evaluate these things, right? Because this is free of our parameter. But if this distribution, so going back to this, if this distribution that we're using has lambda in it, we can't actually find the upper bound, and we can't find the lower bound. Yep, I'll just turn my PowerPoint on. We can't actually find the lower bound, we can't actually find the upper bound. So we need to somehow make this distribution free of lambda. But looking back at the question, it actually gives us a bit of a hint. Let's go all the way back. You may assume the scale property of the gamma distribution. So the scale property is a way we can manipulate the gamma distribution. So specifically, where were we? We'll look at this basically down. So basically, so far we've done this. So t has distribution 1n, 1 on lambda n. And what that means is we need to reduce this to a distribution that is free of lambda. So hopefully that's really clear. We can't go around with a distribution that actually has lambda in it because we don't know what lambda is. Right, so using the scale property of the lambda distribution, we can actually multiply through by lambda. So the scale property says that if we have gamma AB and we multiply this by c, well, the c actually comes inside to the second parameter. Right? So if we want to get rid of lambda, well, it stands to reason that we can just multiply through by lambda, and that'll cancel out on the bottom. So then we get lambda on t is actually gamma n 1 minus n, 1 on n distributed. So if we go back to what we were saying before, right? We want to find the lower bound and the upper bound. That means that we know that lambda on t lies between, let's just write this out, lies between these two things, because we want to find a 95% confidence interval. So this is our gamma distribution. Then basically we want to have two cots, such that inside we have 95%, and on the bottom we have 2.5%, and on the top we have 2.5%. So in other words, we know that lambda on t lies between these two quantiles. So Q gamma and 1 on n at 2.5%, and then the Q gamma with 97.5%. So that means that this thing happens with probability 0.95. So moving down, we know that the probability of lambda on t being between these two quantiles is equal to 0.95. Multiply through by t, and then we get our confidence interval over here. Right, so don't forget that t is actually just equal to pi on n times this thing. So then our confidence interval is just this thing over here. Cool. So hopefully those steps make sense. Let's just revise them. Number 1, find an estimator, and then basically try to reduce it to a distribution that is free of the parameter. Then find the relevant quantiles of that distribution, and then rearrange the event to make lambda your subject. And that's your confidence interval. Cool. Now we're going to talk about something very quickly, called the maximum likelihood estimator. And the reason why we're talking about this is because it gives us a really nice way to create confidence intervals. So let's just say we have another PDF that's dependent on theta. And again, we're trying to estimate theta. So we define the likelihood function as the product of the PDFs, right? It seems a bit weird. Why is the product of the PDFs a function of lambda? Well, yes, it does have lambda in it, right? So for example, we had like, let's just say we've got the exponential theta distribution. The PDF of this is equal to 1 on theta, e to the minus x on theta. And that can be thought of as a function of lambda, because this tells you the density of x given a certain lambda. So if this thing is high, it means that the value of x that you got is really likely under lambda. So you can think of this as a function of lambda as well. And that means you also think of x1 all the way down to xn as constants. Right, that's a likelihood function. And the log likelihood function is actually equal to the log of this product. The reason why we care about the log likelihood is because products are a bit annoying, because when we differentiate products, for example, you have to use the product rule. But if you differentiate a sum, it's just equal to the sum of the derivatives. So instead we take the log likelihood, and we can actually express it as the sum of the log likelihoods of the individual events. Okay, so why do we care about this? Because this gives us a nice way to estimate likelihoods, estimate parameters. So the maximum likelihood estimator is, as the name suggests, the number for theta that maximizes the likelihood function, right? So if you graph the likelihood function, for different values of theta, well, there's going to be some value most of the time that maximizes it, right? So that's going to be called the maximum likelihood estimator. And we call it the argmax. Basically it just means, this is just a fancy way of saying the number that maximizes it. It's not that complicated, but basically it's the value that makes this graph the highest. And because we talked about log likelihood functions, the argmax of capital L, which is the actual likelihood, is equal to the argmax of the log likelihood. In other words, if a certain point theta maximizes capital L, or if it maximizes lowercase l, then that actually implies it maximizes capital L, right? Because, well, if a number is higher, its log is going to be higher, and if the log of something is higher, it itself is going to be higher. So you can maximize either of them, and it'll give you the same result. And that's really useful because, as I said, you can't really easily differentiate the likelihood, but you can really easily differentiate the log likelihood. So because this is easier to differentiate and therefore find a maximum of, you can find the max of this, and that gives you the MLE. All right, let's do an example. So the Pareto distribution. This is often used to model the distribution of wealth, and it has this density function. Yada, yada, yada. Let's find the MLE of it. Okay, so the first step of finding an MLE is always just to actually find the likelihood function. So let's construct the likelihood function L alpha. Okay, so we've got these, we've got observations x1 down to x2, xn I should say. And basically it's going to be the product of the PDFs at those values x in terms of alpha. Right, so the first one will be alpha times x1. The second one is going to be alpha x2. Then we have alpha x3. And so on. Cool. Right, that's pretty good. But it's going to be a bit hard to differentiate, so what we might do instead is we might actually take the log likelihood. But let's just do this first. Okay. So basically a nice way is to group it together. We've got a to the power of n, and we've got x1 down to xn, or to the power of minus alpha plus 1, which is what we have here. Then we can differentiate, and to differentiate we just use our index laws. So we've got n times ln alpha minus alpha plus 1 times the sum of the lns. And you can see this is a lot easier than trying to differentiate. I'm trying to differentiate this, because now all we have to do is just differentiate a sum of logs. Right, and remember we differentiate with respect to alpha because we're trying to find the maximum of L under alpha. So we do n divided by alpha minus the sum. Alright, and so as you probably remember from first year calculus, the next play over here is just to set this equal to 0. Right, so if dl on d alpha is equal to 0, then that means that n on alpha minus the sum is equal to 0. And basically solving for alpha, we get this. Cool. Alright, so that's basically formalizing this approach. We just divide through, and we're almost done. Okay, so this thing is also a very important thing. We have solved for this being equal to 0, but we haven't actually shown that it maximizes the likelihood. And to do that, we actually need to check the second order condition, which is the second derivative with respect to alpha. Oh, I think my thing actually froze. Give me just 1 second. Alright, I think we're back on. That was fun. Okay, alright, so back on maximum likelihood estimators. So, yeah, we've basically solved for when this is equal to 0, this derivative is equal to 0. It's equal to n on alpha is equal to this sum. So just flip it around, we get alpha on n is equal to this, is equal to 1 on the sum. And then just multiply through by n. And then what happens is basically you've solved for it to be equal to 0. And that's not enough to maximize, because to maximize you also need the second derivative to be less than 0. So just differentiating one more time, this all disappears, and you just get minus n on alpha squared. And so that is less than 0, so indeed that is our maximum likelihood estimator. And we're basically good to go. I'll just move this to the side so my face is not blocking important information. Cool. Alrighty, so that's how we find MLEs, just differentiate the log likelihood function, right? But to actually work with the MLE, we need to know its properties. So number one, it has consistency. So the MLE converges in probability to the actual value of the parameter. This second property is called invariance. So if you've estimated the parameter, we can actually show that even if you take some function of the parameter, so like the parameter squared, it's approximately equal to that thing squared. So we say that g of the parameter, g of the estimator is the MLE of g of the estimator, of the parameter. I'll say that again. G of the estimator is the MLE of g of the parameter, right? So that's called invariance under functions. The third one is asymptotic normality. So it's actually true that the difference between this estimator and the actual parameter divided by the standard error is approximately normal, right? But to work with this a bit more, we need to know the standard error. So that's what we'll talk about now. Okay. So to work out the standard error itself, we need to know this concept called the Fisher score. So the Fisher score is the derivative of the log likelihood function with respect to theta. Right, and the Fisher information is equal to the Fisher score squared, the expectation of that. Right, so the expectation of the Fisher score squared. And there's also a second formula you can use for it. It can be shown that these two are equivalent. So either you can just square the first derivative, or you can take the second derivative and take the minus of that. Okay? And so that's the Fisher information. The expectation of that is equal to the Fisher information. And so once we have the Fisher information, the standard error approaches 1 divided by the square root of the Fisher information. Right? And that means if we actually sub this in, we actually get the estimator minus the parameter divided by 1 divided by Fisher information, the square root of that. So that if that is n01, then also we simplify it a bit. We just get the square root of the Fisher information times this approaches n01. Cool. And this is where invariance comes in. So let's just do our setup. We have theta hat n, the MLE of theta, and let g be a function that is differentiable in the neighborhood of theta. Then, as we get really, really big, as n approaches infinity, the standard error of this function is approximately equal, this should, by the way, say, I'll just correct this, should be the absolute value. The standard error of that is equal to the derivative of g divided by the Fisher information. Right? And that means that you can actually use this. So if you want to find the distribution of a function of the MLE, then you just use this formula here. Okay? So it's very similar to the delta method. In fact, it comes from the delta method, because you can see the variance is scaled up by g prime of theta. Okay, cool. So a quick example, this over here. The Fisher information of this distribution is just equal to n divided by theta squared. So all you have to do is just take 1 divided by the Fisher information square root, and you get this. And that means that the parameter, the estimator minus the parameter, divided by the parameter divided by root n is approximately n01. Right, so all we've done is we've just taken this minus the mean divided by the SD, n01. And the question asks us to find the distribution of theta hat itself. So really all you have to do is just multiply through by this. So times that by theta squared on n, then add theta, and you'll get this. Okay, and you're good to go. Alright, so now we're talking about what we're really trying to get at with confidence intervals. So if you do have an MLE, that's an estimator, then because it's asymptotically normal, the confidence interval looks a lot like the normal confidence interval from before. Because we've got this thing, the center, which is the estimator. We subtract the quantile, 1 minus alpha on 2, which we've seen before, and we multiply that by the standard error. Then we add that again. And that's an approximate 1 minus alpha times 100% confidence interval for theta for large N. Right? And you can also calculate the standard error by subbing in this formula. Okay? So it makes sense because it's similar to our normal confidence interval from before, but basically the idea is that as we get really, really big, you can use this confidence interval called the walled confidence interval to approximate how sure you are that the parameter lies between two numbers. And this is a nice property of the MLE. So this thing is called the Kramer-Rao lower bound. So 1 divided by the Fisher information, which if you recall was actually the variance of our MLE as n approaches infinity, is actually the lowest possible value of the variance for any unbiased estimator. So it means that the MLE is asymptotically optimal. As you approach infinity, the MLE is like the best you're going to get, right? Because it's unbiased, or it's approximately unbiased, and also it's got a very low variance. It's got the lowest possible variance of all unbiased estimators. Okay, so we'll do an example of calculating the Fisher information, and this is a nice example. Because we did this before, we already calculated the MLE. Now let's do the Fisher information. Okay, so basically we already did the log likelihood, and if you recall, there are two formulae for the Fisher information. The first one is the expectation of the derivative squared, and the second one is the expectation of minus the second derivative. Most of the time this second one is easier, so let's just do the second derivative. Second derivative, we end up with minus n on alpha squared, just by differentiating it again. So all we have to do is just take the expectation of that, take the minus, and then we got n on alpha squared. So it looks a bit weird that we're taking the expectation of something and we just get the same thing, but it's because there are no x's in here. If this second derivative had x's in it, we might need to use some of the expectation formulae we have about x, but in this case it's just equal to n on alpha squared. Cool. And they want us to construct an approximate 90% confidence interval. So in this case, alpha, well I shouldn't say alpha because we've got like an alpha we're estimating. Let's just say like, this is a 1 minus 0.01% confidence interval. Right, so that means that our alpha thing from before is equal to 0.1, and that means that we need 0.0, I'm sorry, it's not equal to 0.01, it's equal to 0.1, because it's 90%. That means that we need 0.05 on the other side. So our approximate confidence interval is equal to this. So it's equal to the estimator minus the standard error times this quantile, plus the standard error times this quantile. Okay? And this is called a walled confidence interval. Cool. Alrighty, so we won't go too much into this, but basically you can extend this to multiple variables. So for example, Lebo for 2901 has said that this won't be examined. It won't come up in your exam, but it's good to know because basically it means that even if we're estimating multiple parameters, we have a Fisher information matrix that's basically made up of second derivative terms. So if you've done 2011 or 2111, you'll know this is called a second order partial derivative. And even with multiple parameters, we know that this is going to be asymptotically normal, right? So our estimate is just going to be equal to this. Cool. We'll move on to the last section called hypothesis testing, and this is the most practical part of the course. So it's talking about two things, a null hypothesis and an alternative hypothesis. Okay? So the null hypothesis, which is labeled H0, is basically a claim about what we're observing. So if I say I'm observing people's heights, and my claim is that mu is equal to 1.8. So the average male height, for example, is 1.8, or the average female height is 1.65. Right? Basically, the null hypothesis is a claim about a certain parameter. The alternative hypothesis is what we think might be true if that's not true. Right? So if we don't think that the null hypothesis is true, if we test it out and it doesn't quite work for us, then we'll accept what's called the alternative hypothesis. Right? And there are three possible forms that we generally have. The first one is theta equals theta 0. The second one is theta is greater than theta 0. And the third one is theta is less than theta 0. So let's just think about what that means. Let's just say, basically we're observing heights, and we notice that let's just say someone has told us that the average male height is 1.8. But we go around the world and we notice that actually people are pretty short on average, right? Let me just check. I think we disconnected again. Just give me 1 second while I set this up. That's looking a lot better. A lot of technical difficulties, unfortunately, but it looks like we're good to go. Cool. Alrighty. Back to work. So yeah, let's just say we found out that someone told us that the average male height is 1.8, but we did some walking around the world and we found out that people are pretty short, right? So instead we think, I'm going to test if this is true, and my alternative is actually theta mu is less than 1.8, right? That's when we have this presupposition that it's going to be less than 1.8, right? Alternatively, if we're neutral about heights, we think it might be above, it might be below, then our null is actually mu is equal to 1.8, and our alternative is it's not equal to 1.8. And this rather subtly changes the way we do our test, but not by too much, okay? And basically in a hypothesis test, we use our data to test how likely H0 is, right? By measuring how much evidence our data offers against H0 in favor of H1. So we'll do a nice example with the Mythbusters, right? They're testing if toast lands butter side up more often than butter side down more often than butter side up, okay? And they did a trial and they found out that 14 slices of bread landed butter side down, okay? So, well, we might say from this, it does seem to be the case that toast lies butter side down more often, because in this trial we got 14 down, we got 10 up, right? But we can't just say that just because there are more on this particular occasion, that that's going to be true regardless, right? We have to basically see how likely it is or how strong our evidence is. And that's what a hypothesis test does, right? So our method is to state these two hypotheses we talked about, the null and the alternative. And then basically we try to use our data to answer the question, how much evidence is there against our null? Then we find a statistic. What is a statistic again? It takes x1 down to xn and gives us a certain number out, right? So we try to find a test statistic that measures how far our observed values differ from what is expected under the null. So for example, in this example with butter side up, our test statistic is actually just the number of slices of bread that land butter side down. So this number n is our test statistic. And then we calculate what's called the p-value. The p-value is the probability of observing a test statistic that is just as extreme as the observed value. So what does extreme mean? Well, in this case, we got n equals 14. Extreme means something that's just as extreme as this, but we're trying to measure how much evidence we have for the alternative hypothesis under the null hypothesis. So the probability of being more extreme is actually the probability that we got more evidence that it lands bottom side down. So it's actually the probability that n is greater than or equal to 14. Right, so we'll go through that more rigorously later, but that's what a p-value is. And if this value is really low, it basically means that the value we got was really, really extreme, right? If, for example, p n is greater than or equal to 14 is equal to 0.01, that means that we got a value that such that there's a less than 1% probability that we got something that extreme. So we are more likely to reject the null. And so we reject the null if this p-value is below our desired threshold. And we'll do an example that will clear that up in a second. And it'll be one of our last examples because we're running low on time. But let's do this, okay? So, p is equal to the probability that toast lands bottom side down. And as I said, we're trying to assess the probability because notice the wording of the question. We're testing whether or not it lands bottom side down more often. So we have this presupposition to believe that it's going to land bottom side down more often. So we test p equals a half against p is greater than a half. And so what we do is we take this test statistic. And so the binomial distribution is a bit annoying. So what we generally tend to do is just take estimator of p minus a half divided by, estimator of p is actually equal to, it's a binomial thing, where we basically have the number, where n is the number that land bottom side down. So n is the number that land bottom side down, and n is the total number. So this is actually our estimator, n on n. Okay, and this is a common sample proportion that you use. Hopefully you've seen it before. Basically, the sample proportion is an estimator of p. And if you've done this kind of stuff before, you know that p hat is actually n, p, and then p, 1 minus p on n distributed. Right. So we try to standardize the test statistic by doing this. So p hat minus p divided by the variance, it approaches n01. And basically at this point, we just sub in our values. And the idea is just to see what our p-value is. Right? So far this is our test statistic. So the question is, how much evidence is there against the null hypothesis? So we're trying to test, again, let's look at our hypotheses. P equals a half, P is greater than a half. Right, so extreme in this case means extreme in a way that supports the alternative. So if we get P is, so what does P is greater than a half imply? It implies that we'll get a ton of toast lying, basically landing bottom side down, right? So basically, extreme means we get just as many landing bottom side down, if not more, right? So that's why our probability is actually this, right? Because we're trying to find something that's extreme in a way that supports the alternative hypothesis, right? If H1, let's just create a new page here. So if H1, let's just take an example, where just P is not equal to a half, then what we could do is basically say, we actually want to find the probability that P is greater than 14 on 24, or something that's very low. So if we get a very low number of toast landing both side up, that also means that P is not equal to a half. So actually, let's write this out. Well, that's why we tend to standardize our test statistic, because if we standardize this, we get Z equals P minus estimator of P. This has N01, and basically if, to say, sorry, this is equal to P on P minus 0.5. Basically, if P is equal to a half, this thing is going to be very, very close to 0. But if P is not equal to a half, right, then it's going to be very far away from 0. So in that case, our p-value would actually be, it can be very, very high or very, very low. So it will be the probability that this thing over here, so absolute value of z, is greater than or equal to the number we observed. Okay. So in other words, if we have a two-sided test, this is called a two-sided test, then basically we can reject, we basically take the probability of it being large in either direction. But in this case, because we just want to find out if it's greater than, a half, we basically take the probability that it's greater than or equal to 14 on 24. Okay, so that's a very brief overview of how that works. But in this case, basically it's summarized by if p is greater than a half, we just take the positive side. But if p were less than a half, we take the negative side. If p were just not equal to a half, we'd have to take both sides and take the absolute value. Right, let's go back to this. So now we want to find out the value of p hat being greater than or equal to 14 on 24. So all we do is we just standardize both sides, and so we end up getting something like this. P hat minus 0.5 is greater than or equal to 14 on 24 minus 0.5. Then we standardize by the variance, or replace this with 0.5. And then basically this thing turns into 0.82. And basically our p-value turns into 0.2071. So what that means is basically we have a 20% chance of getting something this extreme, which means that some of the time we might actually get this result by chance. We might actually get quite a lot of toast lying butter side up, right? We might actually get this proportion of 14 on 24. That's actually not enough evidence, right? Because generally we set our level of significance, which is the threshold, right, beyond which we reject the null hypothesis, to be 0.05, right? So this p-value is basically, we want it to be small if we want to reject, and in this case, most of the time, we reject if it's less than 0.05. But since it's not, we don't reject the null. So if, for example, we had, we did actually get 0.002 as our p-value, that means there's actually a lot of evidence against a null, which means that we do want to reject. Right. Sometimes they'll actually specify a p-value. They'll specify a threshold, so a level of significance. And when they specify a level of significance, that actually means that we want to use that as our level of significance. If they say use level of significance 10%, then basically you only reject if your p-value is less than 0.01. Sorry, 0.1. And that's our conclusion. So because we have too much p-value, our p-value is too big, we don't have evidence against p equals 0.5, so we do actually have to accept our null. Cool. We'll do some examples really quickly, so with normal samples. So basically, when we've got a normal sample where we don't know the mean or the variance, then we want to use the fact that this thing over here, so the sample mean minus the actual mean, divided by s on root n, follows a t-distribution with n minus 1 degrees of freedom. Okay. And so what the result of that is that basically we can calculate the probability of, let's say we want to say mu equals mu 0 versus one of these. So let's just take, for example, this one. If we want to test where mu is not equal to mu 0, then basically, let's just see this. If this thing is really big, this statistic, so x naught minus mu 0 on S under n is really big, then we want to reject values. We want to reject the null. But also, if it's very, very negative, that would also suggest that there's evidence against the null, so we also reject the null. So our hypothesis test in this case is actually using this test statistic and then using the probability of the t-distribution to actually calculate your p-value. So it will make more sense when we actually do it. So let's do this example. Okay, so let's do this example over here. So the daily yield of fertilizer has a mean of 880 before. And since the new machinery was installed, we want to know if the new machinery is more efficient. Okay, so what that means is we're basically testing if the new mean is greater than 880, right? So again, the null is going to be mu equals 880, and the alternative is mu is greater than 880. Okay, cool. So let's have a look at this. We're given n equals 50, we're given the sample mean 888, and we're given the standard deviation 21. So we're going to be using that test statistic. So let's just look at this. This basically measures the deviation from 880. If we sub in this, this measures the deviation from 880. So to calculate the p-value, we're going to calculate what value of this we got, so the value that we got, and basically figure out how unlikely that value is, right? Basically calculate the probability that we get something as extreme as this value, okay? Let's do some more work. So we use the test statistic and we know it's going to be t(n minus 1) distributed. So what we basically do is we say our p-value, let's just remember that, is the probability of getting something more extreme. So it's going to be t is greater than or equal to the value that we actually got. Okay, so let's just think about that though, because with the t distribution, or with the with this example, how do we know it's going to be greater than this? What about if it's a different form, right? So actually, there actually is a very nice way of doing this. Let's look at this for a second. There are actually three cases. Well, let's just compare the two main cases. So x equals 880. There are two possibilities. So h1 is greater than 880. And 2, h1 is not equal to 880. Okay. So in case 1, what we're basically saying is that we think the mean is large. So what that means is that more extreme means larger. So if this value over here, this test statistic, is very large, we want to reject. And that means our p-value is equal to the probability that t is greater than the value of t that we got. Okay. The other case is where the alternative is actually equal to h1 is not equal to 880. So we don't know what the mean is. So no presupposition. So instead of that, our p-value will be the probability that we got t is greater than t, or minus t is less than minus t. In other words, the probability that we got something as large in magnitude as the value that we actually got. This is our two-sided test. Hopefully we'll remember all of this from our lectures. But basically the next step is actually just to calculate the actual number, right? So we want to calculate the probability that t, where t is actually the t n minus 1 distribution, is greater than the value we observed. So sub in everything we got. We got a new sample mean of 888. 888 minus 880 is 8. Divide by s on root n, which is 21 on root 50, and we get t is greater than 2.69. Right? And so the reason why we standardize this is because now we know the distribution of this. We know it's actually tn minus 1. So what happens as a result of that is basically now we've got a probability. Using R, we can use our qt values. So we can find out that this probability is equal to 0.0049, which is less than 0.005. Right? And to do it with R, by the way, you use the pt function. It gives you the t distribution probabilities, and that gives you 0.0049, which is less than 0.005. Cool. And this tells us that if h0 were true, we'd be very, very unlikely to observe something as big as this, so as big as 2.69, right? The probability of that is so small, which means that there's strong evidence against the claim that mu equals 880, and we can reject with level of significance 5%. Cool. So another way to think about this is to find our rejection region. So to find a rejection region, well, let's think about this. This basically means we want to find a region where we'll actually reject the null. So remember our t-distribution. This is our statistic. And remember the t-distribution looks a bit like normal. And basically remember we're rejecting for very high values. So we want to find the value, we want to find the very smallest value such that we'll reject, right? Because we're not going to reject if it's going to be really close to 0, right? But we want to find the first value, the smallest value of t, such that we'll want to reject the null, right? And what is that? Well, the p-value needs to be less than 0.05, right? Which means that the tail probability, or the probability of getting above this value, needs to be 0.05. So that's exactly the definition of the 95th quantile. Because if we find the 95th quantile, then that means that the tail probability is equal to 0.05, which means that we've actually gotten the region such that everything beyond here will start to reject the null. And that's called our rejection region. And they've done this very nicely over here. So QT, 0.9595, it gives us 1.676. That's actually equal to the first value, such that the p-value drops below 0.05. So our rejection region is equal to t is greater than 1.676. Right. And the definition of the rejection region, just the set of values of the test statistic for which we reject h0. Okay, cool. All right, so basically we've reached the close of the course, but we'll start to go through some definitions real quickly. So a power function, which we often write as pi theta, it gives us the probability of rejecting the null hypothesis given that theta takes that particular value. Right, so it's pretty similar to, you can easily just calculate it by subbing in the parameter theta. So for example, pi of 0 is equal to the probability of rejecting given that theta equals 0, right? And you can just sub in theta equals 0, find the probabilities there. Okay, we'll skip through this because of time. The size of the test, which we talked about before, the level of significance, is also known as the supremum of the power function over the viable values of theta for the null hypothesis. So before we basically said that the power function is equal to the probability of rejecting, given theta. And that's really similar to the concept of level of significance, because level of significance is basically the probability that we want of rejecting the null, right? Given that the null is true. So basically what this definition is saying is we want the maximum value of this power function to be less than the level of significance. Or the maximum value of the power function to be less than the level of significance, right? Because what that means is, let's just say that there is some value of theta such that the probability of rejecting is like 20%. Let's just say this is not true. Let's just say, for example, the maximum of the power function is equal to 0.20. Then, well, that's clearly not a good test, because then we have a 20% chance of rejecting the null, even though the null is true. So we actually want the maximum value of this power function to be less than or equal to the level of significance. Okay. Cool. We'll skip through this because it's not the most important test. You can read it through in your own time, but it's called the generalized likelihood test. And we'll skip through this as well. Basically, we'll finish off by quickly talking about the Wald test. So what is the Wald test? The Wald test is just a way of doing hypothesis testing using our MLE, okay? So the Wald test statistic from before is actually defined as this thing. And so let's say we do have a test where we want to test, for example, theta equals theta 0 against theta is not equal to theta 0. Well, then basically we'll reject, let's just take the Wald statistic, which is equal to theta hat minus theta 0 on standard error. Well, if this thing is either really big or really, really negative, so if this thing is really big or really negative, then we'll want to reject the null. So our rejection region is basically, we'll reject for values where the Wald test statistic is very, very large. Right. So basically for a test statistic, for a Wald test, what you want to do is just calculate this statistic over here. And if you get a very, very big value, or a very, very negative value, you want to reject. But how do you quantify at what point you start rejecting? Well, that's when you use the p-value. Okay. So the p-value is the probability that your Wald test statistic is greater than or equal to what you observed. Let's just say you observe a w, you calculate a w, then your p-value is equal to the probability that you got something just as extreme as w. Okay. And because we know that this is actually normal 0, 1, at that point you can start using normal probabilities. Okay. So in this case, we actually got a test statistic of, we can calculate it here, alpha hat is equal to n divided by the sum of the logs. And the sum of the logs is equal to 53.7. Okay. That means that our value for alpha is equal to 100 divided by 53.7. Okay. So in this example, our Wald test statistic is equal to alpha hat minus 1.16, and our standard error in this case is equal to alpha on, well, because we've got the Fisher information here, the standard error is equal to the square root of that, the reciprocal of the square root of that, which is 1 on root alpha squared, 1 on the square root of the Fisher information, which is equal to alpha on root n. Okay, so that means our standard error is equal to alpha on root n, which means that we take the estimator, minus the actual parameter value, and divide by 1.16 on root n, right? And that's our Wald statistic. So in other words, we observed 6.053. Okay, and that means because our world test statistic was just alpha is greater than 1.16, we want to reject for values that tell us that alpha is going to be large. So our p-value and the definition of extreme is equal to this. So the probability that the world test is greater than 6.053. Okay. So that means we can actually easily do normal probabilities. So this is obviously going to be greater than, so the value of this is going to be less than 0.05 because we know the normal distribution, we don't have to calculate it, but 6 standard deviations away from the mean is very, very large, so this is going to be less than 0.05. And there are two ways of doing this. Either we can do that, or we can say that the test statistic lies in the rejection region, which is going to be greater than the 95th percentile, which is 1.644. So that's one way of doing it, or we can do what we just did, which is calculating the p-value. Either way, we reject because it's not going to lie in this normal region. In fact, it will lie in the rejection region because W is just too large. Right. So just to reiterate, the p-value is the probability of getting a normal random variable greater than what we observed, which we can calculate using R, but basically it's less than 0.05. Either way, we reject H0, and we conclude that alpha is greater than 1.16. Okay, so we had to speed run the last bits, but if you have any questions, just let us know. But that's a conclusion to what we did today. We covered a lot of content, but it's all about convergence, all about estimation, and about hypothesis testing. So thank you so much for coming. If you have any feedback, just let us know. It's really, it's not just a tokenistic feedback form, it's really useful for us to know what we could have done better, areas we could have focused on more perhaps, areas that we could have gone over in more depth, just to let us know how the seminar ran. If you have any general feedback about how we could improve the way we run seminars in general, just let us know as well. Scan the QR code if you can, it's really useful for us to know. Okay, and thank you so much for listening. And we hope you learnt a lot about stats and about the course, and we wish you the best of luck for your finals. Right, thanks so much.